All right, folks. Hopefully you're doing this COVID-19 thing right. If you feel like you're going crazy in your house right now, that means you're doing it right. Okay, let's get going here with this lecture. Unless you want to have a little mini dance party first, we can do that. Okay, more of that later. Okay, so I wanted to just summarize the learning goals. We really just only have a couple more to go to finish off this chapter. And if you've been following along with these, great. If not, let's do a review. So we've definitely done learning goal number 1, understand how reaction rates relate to the change in concentration of reactant or product over time, etc. Learning goal number 2, understand the difference between average, instantaneous, and initial rates. Number 3, know how to write a general rate law, etc. Number 4, be able to determine reaction orders and rate laws from the method of initial rates. So make sure that you're okay with this. Learning goal number 4. That's what you're going to do in your virtual lab here coming up. Know the units of rate constant for 0, first, and second order. Know how to use the integrated rate laws, and know the plots needed. So all of these learning goals 5, 6, and 7, that all comes from that summary of reaction orders that I kind of just went through in the previous video. And then now what we're going to do in these last 2 videos, I'm going to make a whole video just on this learning goal number 8, be familiar with the collision model of kinetics, the Arrhenius equation, and diffusion and rate limiting steps, activation energy, etc. And then I'll do a last and final video on this learning goal number 9, be familiar with reaction mechanisms, elementary steps, intermediates, catalysts, and so forth. Okay? All right, let's get this thing out of here, and let's get going here. So this is section 13.4, and this is our very last learning goal. So really quick, just a few definitions, and then we'll learn how to apply these definitions. So the collision model is built on the simple idea that molecules must collide to react. So this discussion we've had on chemical kinetics, thus far, we've really just been talking about experimental methods, how we figure out if something is 0, first, or second order. But we haven't really gotten into like the theory, what we often refer to as first principles. And if you think about it, what needs to happen before a chemical reaction can take place is the molecules need to diffuse to each other and travel and collide. And that takes time. That takes time for things to diffuse and find each other and then collide. And a diffusion limited reaction is the fastest possible reaction. And we think of these things as called rate limiting steps. The rate limiting step in a diffusion limited reaction is the time it takes for molecules to diffuse and collide. So I often like to use the example of driving down to the Bay Area to describe this. So let's say that you've got your Tesla Roadster or your Porsche or whatever, pick your favorite super fast car. And you're trying to drive down to the Bay Area. Friday night, you've got a concert to go to. This was like before all the COVID stuff, right? When you could go to concerts. Yay. So now you're driving down to the Bay Area, you're hauling ass, you're in a super fast car, but then you get stuck behind traffic in Santa Rosa. So does it matter that you have a fast car? No, it doesn't. It doesn't matter how fast you can go. It only matters how slow you can go. You're limited by your rate limiting step. And in this example, your rate limiting step is not how fast your car can go. Your rate limiting step is the traffic in Santa Rosa, or, like me, you always hit traffic on 37. Totally sucks. That's the rate limiting step. That is limiting how long it takes your reaction to go, or in this case, your road trip. Okay? So in a diffusion limited reaction, if the only step involved in the reaction is the molecules finding each other, diffusing, finding each other, collide, and then a reaction happens, that's a very fast reaction. What ends up happening in a lot of chemical reactions is the diffusion is the fast step. So they diffuse, they find each other and they collide, but the reaction's not over. They might have to like dance around, they might have to flirt a little bit with each other, exchange electrons, vibrate around a little bit, and that could take a lot of time. That actually takes a significant amount of time, much more time than it takes for them to just find each other and collide. So we could come up with another cute analogy, you know, falling in love, right? It might take you some time to get to know someone and to meet them and etc. You know, you might not be ready as soon as you just meet each other and collide. And if you do, then you had a diffusion limited reaction and you got things done real fast. Okay, let's move on. So, factors that influence these types of reaction rates or these rate limiting steps. So, temperature. So, more often than not, when you increase the temperature of some molecules, it will increase the speed at which they react. And that's because they have increased kinetic energy, they're moving faster, they can diffuse and find each other faster. In certain instances, temperature can actually have the influence of slowing down a reaction, because what that can do is it might actually make them collide too fast and then bounce off of each other. So that's kind of rare, but it can happen where temperature will actually increased temperature will slow a reaction down. Again, that's rare, but it can happen. More often than not, increased temperature will increase the rate of a reaction. Okay, so there's the activation energy. This is the minimum energy of molecular collisions required to break bonds. So if you think about it, things are going to collide with a certain force. And if they have enough energy in that collision to break bonds and go and form new bonds, then they'll go and react. But they might not have enough collisional energy to do that. So the amount, this activation energy, the energy required to break bonds and go on and react, can also limit the rate of a reaction. And then the steric orientation, so when a molecule collides in a way that leads to a successful collision. So I have some pictures that I think will describe the steric orientation a little bit better. But effectively, you have to consider that molecules will have a sweet spot. They have a spot where the new bonds are formed. And if things collide like in the wrong place, it might not lead to a reaction. And whereas if they collide in the right place, it might lead to a reaction. Okay, so let's go and look at some equations and things like this that's going to help us discuss this. So this is the very famous Arrhenius equation. This actually got the very first Nobel Prize in chemistry in 1903, Sven Arrhenius. And so what this equation describes, it gives you a way of calculating a rate constant theoretically. So we talked about in the previous slide that all these things like rate constants, reaction orders, etc., they need to be determined experimentally, which they do. But these things can also be done theoretically, and you know, confirming what theory and experiment shows. If your theory and your experiment show the same thing, then you've got a good equation and you've got a good mechanism. So let's discuss this equation a little bit further. So it says the rate constant K equals this collision frequency factor A. Here my notation where that says EXP, that's the same thing as saying E raised to the power negative activation energy divided by RT. Okay, so this is my activation energy. That's that minimum energy needed for reaction. R, that's my gas constant. And of course, that's going to be the 8.314 joules per mole K. So that means temperature has to be in units of Kelvin. And so what that means is my activation energy is in joules per mole or kilojoules per mole. Either one is okay, but recognize when you're doing calculations with this, if you have R in joule per mole K, you've got to have your activation energy in joule per mole. And we note that activation energies, EA, they're always positive quantities. It always takes an input of energy to activate a reaction. And if you think about that, like a really good example of this would be like lighting your Bunsen burner, right? You mix your methane and your oxygen, but there's no reaction, they're not combusting. So you give it that little spark, you give it that activation energy, and then that reaction proceeds spontaneously. Okay, So let's see, what else can I say about this? So a few things. Okay, so a couple things to consider. So what if, let's say, what if the activation energy equals 0? What does that do to the rate constant? Okay, well, if you think about this for a minute, if that was equal to 0, then you have e to the 0 power. Anything to the 0 power is 1. So then therefore k would equal a. And this tells us exactly what a, this collision frequency factor, is. In the limit in which there is no activation energy, and so in other words, the molecules react as soon as they collide. They collide and they react. So in other words, the rate limiting step was the amount of time it took them to just get together in the first place. Okay? Then that means this is the fastest possible rate constant. That's what A represents. It's the collision frequency factor. It's how often something collides. And if you think about this specifically with the first order reaction, for example, if the units here are 1/2, then the units of the frequency factor also have to be 1/2. And that's a frequency. That's units of a frequency. Or even if it was second order and K is 1/molarity per second, then the A is also going to be 1/molarity per second, which does represent a frequency because it is the 1/seconds. All right. So let's see. What else could I say here? Oh, yes. And of course, because we really like making lines out of things in chemistry, that makes our analysis easier. If here we take the natural log of K, then you can see what we get out of this thing is a line. And I'll talk about this momentarily, but these two equations are the same, right? This is just how we make a line out of this equation. Okay, so let's move forward. So this is a pictorial example of what the activation energy looks like. So I'll just kind of redraw this same graph here that's on the notes. So here, if this is energy going up, and this is the reaction progress, let's say time. So if we're starting at reactants right here, they have a certain amount of energy, and we end at products here, you can see that this reaction would be overall exothermic, right? There's my delta H from initial conditions to final conditions. However, if this reaction requires an activation energy, which most reactions do, it's actually going to have some input of energy before it can go out and release that reaction enthalpy. Okay? So if this is your delta H on this graph right here, from this state to this state, then from here to here, that represents my activation energy. Okay? And at this point right here, as indicated on the graph, that's what we call our activated complex or our transition state. Okay? So if, for example, we have molecule A and B reacting, all right, and this will say this is my initial state. So they go on and react and make some kind of like transition state. Let me make that a little bit more clear. So I'll say like ... So this would be the transition state that's often given with this double dagger symbol. Okay, that's my transition state. And this is the state that requires activation energy to get over. Okay? And so then finally, these might go on to react to form molecule C in the final state. So if this is A plus B, and this is C, they've got to move through some temporary transition state where maybe they're in close proximity to each other, but they are in the process of exchanging electrons and making new bonds, etc. Once they have enough activation energy to get over this hill, then they can go on to form products. All right. So I'll show you a few examples. Let's see here. Actually, no, I'm going to keep drawing a few more things on this activation energy diagram let's look at a couple cases. Let me make this nice and big, and I can show you a couple of different examples of how this works. Energy going up, reaction progress going this way. So suppose, again, we had reactants I and products final state, and we have some activation energy. Okay. So now, if let's say, so this, as we can see, is an exothermic reaction, right? Because we've got delta H going down right here. Okay. So what if I had something that looked like this? What if I was starting here? So this is like some different reaction, right? Actually, I'll do this on another slide. Let's keep going with this exothermic reaction. So now suppose I had a reaction that proceeded much faster. So that would tell me that it had to have a lower activation energy. Okay. So if I think of this several different reactions, here's reaction number 1. Here's maybe reaction pathway number 2, and here's reaction number 3. All right, we could definitely say that EA for reaction number 1 is greater than EA for reaction number 2, is greater than EA for reaction number 3. And so what that means is reaction 3 is going to proceed the fastest. Reaction 1 is going to proceed the slowest. So the reaction with the lower the activation energy, the faster the reaction will go. Okay. So now let's look at this in the case. So this is a exothermic reaction. Okay, I'll pause for just a minute so you can write that down. Okay, so let's look at the case of an endothermic reaction, a reaction that requires an input of energy. So we might start down here with reactants and end here with products in the final state, and then we'll have some activation energy that looks like this. Okay, and so what you can see in this case, this was still my delta H for the reaction, so it's a positive quantity now. But now my activation energy doesn't start up here, it actually starts way down there. Okay, so my activation energy for an endothermic reaction also includes the delta H of that reaction. Okay, so just keep that in mind when we're looking at these kinds of graphs. How to tell the difference between an endothermic and exothermic, and how we get the delta H and the activation energy from these types of diagrams. Okay, so I'm going to move forward, and I'm going to talk about this whole steric orientation and this activated complex, or this transition state here. So this is a good example of the reaction between ozone and nitrogen monoxide to form oxygen and nitrogen dioxide. And what you can see here, what has to happen in this reaction when, so you're exchanging an oxygen atom from the ozone to the NO. All right. So if I look at this, you know, I'll kind of draw the same thing that's going on here in the diagram. So here in this reaction, right, I'm not doing the correct Lewis structures just to make this easier. So they need to collide with the oxygen and the nitrogen oriented with each other, because ultimately what you end up making is a new oxygen-nitrogen bond, right? So as you can see, if these, so this is now showing you, you know, if they collide like this with the oxygen and the nitrogen oriented to each other, right? That's not going to make a new bond between the oxygen and the oxygen. So that's why that is not an effective collision, or it's why it says it's an ineffective collision, because they're not colliding in the right orientation to give you the correct products. So oftentimes with small molecules, steric orientation is not as important, because if you think about the size of either of these molecules, you know, you could come in from an angle or something like that, and the nitrogen and oxygen would still be oriented. With bigger molecules, with macromolecules, like proteins or amino acids, or if you think about in the case of pharmaceutical molecules, right, where you take some type of drug and it has to land in a very, very specific pocket, right, that actually can be very slow, because the molecule has to really work its way and find its way into a very specific orientation. So oftentimes with small molecules, steric orientation isn't as important. However, with large molecules, steric orientation is very important. Okay. So let's see, moving along. So here's a real example of what we just talked about. And you can see here, this is a very exothermic reaction with a really small activation energy. It's the same reaction that we were just talking about, okay? And it's showing you this nice picture here in the activated complex where at the same time you have this oxygen from the O3 bond breaking and the oxygen from the NO molecule forming. So that's what ends up being like a time sink for these reactions. And what I kind of mentioned earlier, when the molecules are like flirting or dancing around with each other or whatever, they're taking time to reorient and react. And so even though this is a small activation energy, 10.5 kilojoule per mole, it would still limit the amount of time, or I should say it would lengthen the amount of time this reaction needs. And let's see here. Going to the next slide. So now if we look at the same reaction but try to reverse it, okay? So this is the exact same reaction but now reversed. So now NO2 and O2 are reacting to form NO and O3. So you can see this activation energy is now humongous because it included that little tiny bit right there, but it also included that entire delta H, all right? And so this, as you can see, this activation energy, there's a deep connection with this and equilibrium, okay? And so I'll write an approximate equation right here. So if we have a reaction, let's say, I'll use the same reaction we've been talking about, NO plus O3 is in equilibrium with NO2 and O2. So we talked about this reaction going forward and reverse, and I'll write the forward as K forward and the reverse as K reverse. So if you think about this thing, equilibrium is going to be established by how likely it is to go forward or reverse, right? And so if we think about an equilibrium constant, we know the equilibrium constant for this reaction is going to be concentration of NO2 over O2 divided by the concentration of NO over O3. Well, these things are starting to look strikingly similar to the rate laws, right? So if you recall in the rate law, if let's say this is first order in NO and first order in O3, the rate's going to be K times NO times O3, okay? And then once these all achieve equilibrium, we know the concentrations are going to stop changing. So there's an approximate expression that we can come up with for equilibrium and kinetics, and that is that an equilibrium constant is the ratio of the forward reaction over the reverse reaction. So what you can see then is if you have a K greater than 1, that means the forward rate constant has to be greater than the reverse rate constant. In other words, products are preferred. Now, in the event where the K is less than 1, that means that K reverse has to be greater than K forward. And in that case, that means that reactants are preferred. Okay? So I don't think I had this specifically in the learning goal, but I think that just having a general idea of this equilibrium constant is K forward over K reverse, a general idea of that is really useful for you. Okay, and then let's see. I think just a couple more things for this video, so I'm going to move the slide here. Okay, great. So you can determine the activation energy experimentally, and this is another thing that you're going to do in your virtual lab. So if you basically what you do is you would do several different experiments at different temperatures. And the idea would be in each of these experiments, you want to keep everything the same except the temperature. So you would try to keep concentrations the same, the reaction conditions the same, except for you vary the temperatures. And what you would get then, because the rate constant is going to change with temperature, you would get a whole bunch of different rate constants. And then now, based on this equation that I mentioned previously, if you then take 1 over the temperature versus the natural log of all of your k's, like this graph shows, natural log of k and 1 over temperature, then you would get several data points like so, 1, 2, 3, and 4, and it would make a straight line when plotted as natural log of k versus 1 over t. And you can see based on this equation right here, the slope of this line, so this is very similar to thermo, the slope of that line is going to be equal to negative EA divided by R. And because all activation energies are positive, you're always going to have a negative slope from this thing. So negative negative equals a positive. So when you say R 8.314 times the value of your slope, this gives you the activation energy, which is, again, is what you're going to have to do in your lab. And also, this is very similar to what we did in thermo as well with equilibrium. I'm just going to talk about this equation briefly. We could calculate any one rate constant by using now this form of the equation. So for example, I could do the graphical analysis and get the slope. And that would be very straightforward. And there's a problem in your smart work that's what it's going to do. It's going to give you several different rate constants and temperatures, right? 1, 2, 3, 1, 2, 3, etc. Perform this analysis, fit the slope, and that will give you the K. Another thing that you could do is, if let's say you know the temperature at this data point, and you know the temperature at this data point, and also you know the K at that data point, and you know the K at that data point, then, right, so I'll say, if you have any one set of points, then you would use this equation, and that's how you could also solve for the activation energy. Okay. All right, folks, I think that finishes it off for this video. I'm going to do one more video in this kinetics chapter on mechanisms, and then you'll have just another quiz to do, a part 2 quiz that's based off of the 3 videos that I'm recording for this particular week. All right, folks, I'll see you later.